Okay, this is the second of the 3 video segments that I'm posting on the subject of thermal analysis of some laminated composites when it's done in CATIA's native FEA solver. Okay, the first one was already posted, and it was a simple problem consisting of a laminated balanced strip of composite made of 6 layers, and because of the nature of the symmetry and balancing, this was only during the cool down, taking it from the oven. It was primarily in plane shrinking and no bending. Okay, this one is a cross ply, and it's non-symmetric because it's only 2 plies, and one of them is 0 degree, the other one is 90 degrees. Okay, so it is still balanced because there's only 0 and 90. 0 and 90 plies are balanced. Okay, so let me put this thing in the uh, slide mode. Okay, so the geometry is still the same. In other words, the strip which is 4 by 1 inches, it consists of 2 plies. Each one is 0.01 inch in thickness, and uh, this is made of carbon epoxy, and you put it in the oven, raise the temperature to 270 degrees. You're assuming that it cools at 270 degrees, and then you take it out of the oven and place it in the room temperature, which is 70 degrees. Therefore, there is a temperature drop of uh, of 200 degrees. Okay, so what we'd like to know is what is the after it cools down to that 70 degrees temperature, what is the stresses in the in the in the in the composite. Okay, now there's no mechanical load here. The third video segment is going to be a combination of cool down or thermal loading and a mechanical load also. That's going to be the third one, which is coming up soon. Okay, so it's not drawn to scale, and it's got 2 plies. The bottom one is 0 degrees, top one is 90 degrees. Okay, and this drawing is not to scale because 4 by 1, there's no way this can be 0.01 inch. Okay, now this problem was done analytically in that site, except that the coefficient of thermal expansion in the fiber direction was taken to be negative. However, CATIA will not take a negative value. Therefore, I'm going to assume, because this is a very small number compared to alpha 2, about 100 times smaller, I'm going to take this thing to be 0. The other thing that you should realize is that this coefficient in my database is going to be described as degrees per degree Fahrenheit, but I have to convert that to per degree Kelvin because in CATIA, the coefficient of thermal expansion, I could not change the unit of it so that it reads as per degree Fahrenheit. So I have to make this correction here, make conversion here. So multiply this thing by 9/5, which comes from the formula, conversion from Fahrenheit to Celsius. And this is the value that I'm going to be inputting. The second thing is that this thing is going to move out of plane, basically bends. Okay, and that's why there are curvatures there in that site where the hand calculation is done. Actually, this is a screenshot of that particular calculation, but this number is not correct. I look at the presenter's Excel worksheet spreadsheet. These numbers are not on the spreadsheet. There are 2 other numbers that are there, and they're these numbers. Okay, so this is a mistake. We're going to be comparing the curvature with this information, and now also the strains are given. Strains are given in that screenshot of the fellow's work, but these are in-plane strains. In CATIA, at least to the best of my knowledge, and I couldn't find anything contrary to that, the in-plane strains are not provided to you. The in-plane curvatures are, but the in-plane strains are not provided to you. So in order to compare this guy's work with what Catia does, I have to calculate the strains based on the in-plane strains, which are here, and that's the classical lamination theory formula for each ply. One of the plies have the mid-center, mid plane of the top ply, for example, is half of the thickness of the ply, 0.005. Remember, the thickness of the ply is 0.01. Okay, half of it is this, and you plug in your Z here, you plug in these numbers, and these are the strains at the lamina, at the top lamina, and then when you put a plus 0.05, it's going to give you the strains in the bottom lamina. So these I can get out of Catia, but not directly that fellow. And we're going to see how well it compares with the results there. Now, the bottom line is that if you take the ply out of the oven and you let it sit there, cool down, it's going to bend. This used to be a flat, a flat, a flat composite, okay, composite strip, but it's going to bend. Now, these are going to be done in 2018, and in the previous video segment, I mentioned that if you're doing this thing with other versions, earlier versions perhaps, be careful because the stresses, there's quite a few bugs in different places, with particularly the plotting of the stress components. And so I'm pretty sure that these are corrected in version 2018. There may be other bugs, but not definitely plotting stresses. So although it runs and you get the same deflection and the von Mises stress, but you've got to be careful about the specific components of the stress. Okay. All right. So let me move this thing down. Keep it handy. Yep. First thing I want to do is I want to create my material database. So it's going to be start, infrastructure, and material. I've done this thing many times throughout the last 14 or 15 videos that I've provided. So this is going to be, let me give the name of it, my second video thermal. Okay, and composite. The acute thickness is 0.01. Okay, that is right there, 0.01 inch. Okay, and this is going to be unidirectional. Okay, and apply. As for material, click on the analysis, select 2D orthotropic, and for longitudinal, it's 20 million, 2 e to the 6. For transverse modulus, 1.2 e to the 6. Poisson ratio, 0.25. Shear modulus in the XY plane, 800,000. 1, 2, 3, 4, 5. And in the other two plane, 400,000. 1, 2, 3, 4, 5. And 4, 1, 2, 3, 4, 5. Okay. As for the coefficient of thermal expansion, right down here, the first one, longitudinal, I'm assuming it's 0. Remember, in that reference that I'm getting the numbers from, it's assumed that it's a negative one. But if you put a negative number here, you'll get an error message. It doesn't even tell you what the error message is, but it won't run, okay? And for here, I already made the conversion, 2.808 e to the minus 5. That's what this thing was, right? Right there, 2.808 e to the minus 5. Okay, very good. And apply, and okay. And we're going to save this. I created a folder on my desktop. It was called my second thermal video, and I'm going to call it my second, just the name, thermal run. Okay, run. So it's going to go into that folder. Very good. Okay, we can close this. Now we're gonna Now we're gonna now we're gonna create our part file. Okay, so under generative shape design, on the horizontal plane, I will sketch a strip which is 4 by 1, 4 inch by 1 inch. Exit, fillet, FIL, join it. That's my favorite thing to do. Double click on it. Oops, cancel. Did I join this? Let me see for a second. What did I join? I wanted to join the, not the sketch, the surface. Okay, so let me replace this. Remove this. For join, I want to select that surface FILL. Maybe I cancel this. How about delete? Okay, do it again. Join, fill. Okay, double click, flip the arrow. Flipping the arrow means that the shell elements that are going to be created on the surface, their normal is going to be opposite to this red one that I just flipped. Okay. This is not a necessary step, absolutely necessary step, but I like to do that for good reasons. Okay, so now we're going to create a coordinate system that will be used as a rosette, so axis system. Uh, Default is placing it at the global origin 0, 0, 0, but I want to move this thing a little bit to the left so that I can see it better. So I'm going to create a point and I'm going to move this in the position -2 for Y, okay? And I'm going to uncheck the current so that from now on, this is not going to be used as the global coordinate, as the coordinate system. Just the global one will be used. All right, save everything. So file, save management. This is my part, save as. It's going to go into that folder that I created. Remember, this thing, material database is here too. Say OK. We are done as far as the geometry creation is. So we're going to go to composite design, parameters. See that? Composite parameters. Add a material. I go to that folder that I created my material. It was called my second thermal video, and it was this thing. And there is only this material in it. Remember, this is the one that I changed it. I named it my second thermal video, whatever. The Q thickness I changed it to 0.05. Now, as far as direction goes, all we need is direction 0 and 90. These are default values, which I don't have to add anything to it. So rosette, you add a rosette, and you select the thing that you created right there. Let me hide this thing, and we say OK, and we're good. Okay, so now we're going to create our plies. So this is just 2 plies, very easy. We can do that manually. So I'm going to create my ply group right there. See that? Ply group. The surface is the one that I joined. The draping direction, I flip it up. So what that means is that the first ply that I'm going to create in this drawing was 0. Then the second one, which is 90 degrees, is going to be on top of that in this direction. That's really what it means, okay? So, and lock the plies draping direction. Okay, very good. So let's start with the first one. And the first one, this is going to be ply right there, ply. It says, where is the group that you want to add it to? Well, I want to add it to this. And the contour of it is going to be that sketch. See that? And then the attribute is going to be 0. Okay, that is supposed to be, the bottom one is 0, so that's good. Say OK. For the second one, you click on the apply again, select the group. For the contour, we select the sketch, and for the attribute, we select 90 degrees. Material is already set because I set it on the Ply Group. Okay. All right, that's good. So here are the two plies that I created, ply 1 and ply 2. You can always look at these by the ply exploder. Apply. The gray one is the default color for 0 degrees, and the blue one is the default color for 90 degrees. So this is good. Did it the right way. And we're going to save it. All right. So now we're going to go to the advanced meshing tools. And you're going to mesh it with the surface mesher. We're going to mesh this. And this is going to be 0.125. And mesh it. Zap it. And you're done. Exit. Let's go to the generative structure analysis. Why don't we look at our mesh? Right there. Change the rendering. There we are. Looks good. So deactivate this mesh. Okay, so that takes care of this, and then we are pretty much done here. So first thing that we need to do is to specify temperature of the reference temperature. Well, first we specify the temperature of this uh, composite, and you select that. Of course, I set 70 degrees. Okay. The reason it's set 70 degrees already is because when I did the other video segment, it was 70, so it remembers these things. Okay, now we have to, as soon as I do that, as soon as I specify the load, temperature, the thermal load, it automatically adds a line here which says environment. This is where you set your reference temperature. My reference temperature in this problem is 270 degrees. I'm assuming that at 270 degrees it was sitting in the oven and basically there was no stress in it. Okay, so that is the reference. When I take it out of the oven, it's cooled down and it shrinks, and there are going to be thermal stresses in it. Now, if I run this right now, I will have a problem because this structure is not, there's no restraint on it. I can apply the good old 1, 2, 3 rule just like I did in the other problems, but I can also do that manually automatically by placing an anchor on it, and all that means is isostatic restraint on this object that's free to move as a rigid body. Now what that does is automatically places the 1, 2, 3 rule on some nodes that it takes. A majority of the cases it works, but you got to be careful, make sure that it makes sense what you have done. I didn't have to choose anything. Basically, as soon as I say isostatic restraint, it takes my part and it applies the 1, 2, 3 rule to it. Now, if you want to see that, by the way, what it has done, so it's not hard. So you can go and say, where is this thing? On the restraint, you put the cursor here, or you put the cursor there. I guess you have to run it first. Let's do a quick run here without numbers. I don't want to run the numbers, so just run it for the mesh. When you do that, you can put the cursor right there and say, or you can put the cursor over here and say temperature field visualization on the mesh, uh, or I can put the cursor on the isostatic, right click, um, restraint visualization on the mesh. Now, let me change the rendering here to wireframe, and you can see what happened. What happened is that automatically it picked 3 nodes, one of them fixed in one direction, the other one in 2 direction, and probably there's one at the other end. Yeah, right there, 3 direction. So instead of me doing the 1, 2, 3, it'll automatically do it. And as I said, majority of the cases it works fine, but I do suggest that you look at some of the earlier videos in the FEA portion of the channel to see some anomalies and something you have to worry about. Anyway, so this is fine. Let me change the rendering back to Edge. Okay, good. I'm pretty sure everything is done. Oh, material composite. We didn't import the material. So let me actually deactivate this. Okay. So as a matter of fact, let me try to run it and show you that you get an error message. So if you say run it now, you will get an error message. It says, hey, you didn't give me the 2D properties or 2D properties. Now because this is a composite, 2D property by itself is not going to work. You're going to have to use the import composite property, and it says where is the support? Let me put that plate there. The support is that plate, and we're going to do it by the ply. We don't have any zones here, so we're going to click on the ply and go and select the ply from the tree ply group. Remember, you don't have to select the plies one by one. If you take a ply group, it takes all of those plies, two of them actually. Now, this symmetry means that the 0 and 90-degree plies are going to be placed with respect to this plane symmetrically. So 0 degrees below it, 90 degrees above it, and the thickness is 0.01 for each one of them. Okay, so before we run, let's save file, save management, analysis, save as, in that folder that I'm using for storing my results, and always pray, run it. Okay, it ran without any messages. This is good. The first thing we want to do is look at the displacement field. So if you click on the displacement field here, right there, see that? Right there? It looks like so, okay? Now, a couple of things, and that is, let's change, first of all, the rendering here to, let me double click on this, on the visualization average ISO, and change the shading to material shading. Okay, so it looks like that. As I expected, it will buckle. Well, I shouldn't say really buckle, it will bend. Okay, it'll bend. Now, we want to compare our results with this stuff. Okay, so I want to plot the temperature, not temperature, the contour of the in plane or the curvature of that initial plane. So let's deactivate this, deactivate that. Okay, so we put the cursor on static case solution right there where all the plots are stored. Right click, generate image, curvature, right there. Now what this thing is all numbers, all the curvature values are written in here. Okay, now if you don't like the fact that it looks like this, just look at these. Some of these 0.122, the other ones are negative 0.122. Okay, and you can see that these are in agreement with the curvatures, because this is gonna bend in both directions. There's gonna be a kx, there's gonna be a kx, there's gonna be a ky, but of course there's no twisting. Okay, so it matches these numbers. It matches these numbers. But what I'm gonna do is to see them better, I'm going to deactivate this. My usual thing, create a group. Is that a group, a box group? This box group looks good from previous runs, so we say fine. And we're gonna say show me the curvature, but only show me the stuff in the box group. And hide the box. Okay. So if you look closer, it only shows you the stuff in uh, in that box. So if you double click on the curvature text, and notice that we are plotting, this is kx, ky is going to be plus. Okay, k1 is going to be minus 0.122, k2 is going to be plus 122. Okay, now of course your c12 is going to be all zeros. You can see that these are almost zero, 10 to the minus 8 or something like that. Okay, so let me deactivate this now. Okay, now we put the curvature again. We put the cursor on the static case solution. Right click, another generate image, and this time we're going to do strains. So let me filter this thing according to the strains, and the strains components, strain components right there, nodal values. Say okay. Okay, so let's just look at the stuff in the box. So double click, just select the box. Okay, and incidentally, let me see in the undeformed shape. So here's what happened. Which ply is this? Now, let me double click on this and use ply number one. Ply number one is the one at the bottom, and it's saying 0.00013. Okay, so let's check this, which is this one. Okay, it's there. It's in that range. These are the negative ones, yeah. And if you go to ply 2, it's going to be 0013, two zeros and 13. So it's in line with this stuff. Yes, there is some differences. I realize that, but there we are. Okay. Now, if you go to ply 2, these are both going to be flipped. So if you go to, sorry, that's not what I meant. Just a second. C ply 1, C22, yeah, 00134, two zeros, 135. If you go to ply 2, notice that ply 2, these things are flipped. Okay, these things are flipped. Two zeros and a 1, two zeros and a 1. And if you look at C22, three zeros and a 1, which is in agreement with what I've got here. Okay, so what else do we have? Already talked about the fact that this is going to bend because of the thermal stress and because it's not balanced. No, it's not symmetric. That's what I meant. Okay, and if you run it in other versions of CATIA, be careful about looking at these strains. These are components. Be careful about looking at the components of strain or stress because there are some bugs as far as calculation and display. When I say bugs as far as calculation, you get the same displacement, deflection, the same von Mises stress in different layers, but when you look at components of different things, oh, there have been changes. There have been changes. In this region, most of the stuff is corrected. Okay. That's pretty much it. And don't let these colors scare you because look at this is all numerical round off. These are all the same numbers. All right, folks, good luck. The next one that I'm going to do is going to be a combination of a thermal load. Take it out of the oven, let it there. Residual stresses are going to build up, and then you apply a load to it, and you're going to see different things in your model. Okay.